Okay, hi everyone. Today we're doing exponential growth and decay as well as compound interest. So we're going to have a couple of equations, and let me tell you this. As long as you have the equations, it's just plug and chug, like no joke. These equations are the backbone of solving exponential growth, decay, and compound interest. As long as we have these equations, we're good to go. Now, some of these equations that we're talking about is, let's look at our exponential growth one. Exponential growth. And this idea of exponential growth is stuff growing on itself. Here's an example. Bunnies. I start off with one bunny. Well, if you have one bunny, can you have kids with it? Nope. So if we start with two bunnies, what happens to these two bunnies? They have a bunch of babies. And it's like a bunch, okay? If you guys ever heard they're multiplying like rabbits, because these guys have a bunch of babies. And bunnies don't care if they inbreed with other bunnies. Here's a fact, interesting fact. You've heard of prey animals and predator, right? Is a rabbit a prey or predator? Imagine if a rabbit was a predator. But an animal, like a rabbit, is a prey animal. So predators eat prey, right? And what happens is prey animals always multiply a lot. They always have a lot of kids. Think about rats, bunnies, anything that gets eaten. Why? Because predators have to eat something, and they eat prey. And if you don't have enough kids, guess what? You're going to go extinct pretty quickly. So if you're a prey animal, you always have a lot of kids, and if you're a predator, you have less kids, because you don't want to overpopulate too quickly. Just weird evolution stuff, all right? So once these kids have kids, let's say these guys team up, and they will have a bunch of kids also. So you end up with this explosion. If you guys ever had two bunnies and these bunnies had babies, you had a bunch of babies afterwards. And then afterwards, these babies, if you didn't control the population by now, are going to have more babies. I had a high school friend, like no joke, she had two bunnies. And by the time senior year happened, she had a colony. Okay, she had a colony in her backyard. So how do we model this growth? And this modeled growth is using this equation. A is equal to P naught E to the RT. Sometimes this will be labeled as A equals to P naught E to the KT, where R and K just different letters but meaning exactly the same thing. This is our rate of growth. A rate of growth. Now, why do we use this E? Because this E models what we call continuous growth. Continuous growth. What I mean by continuous growth is, if I look at a population of bunnies or people or anything that's living, can we say that everyone has a baby in January and we only count babies in January? Like all of a sudden January 1st, bam, 50,000 people show up. No. Continuous growth means at any given moment, people are having kids. Your amount is growing at any given moment. And then you can grow that money or that group of people into the population, and we're going to count them and they're going to grow too. And every time we have something grow, it's going to help us grow some more. And it's always continuously growing. We can look at bacteria. Bacteria, we say if we have one bacteria, it's going to split off into two bacteria in, let's say, 20 minutes. Okay? But is it really every 20 minutes? And once I have two bacteria, are these guys going to exactly time 20 minutes? Okay, 3, 2, 1, split! No, you hit a point where you have so much bacteria out there, they're just constantly growing, and now it seems like at some random interval. Okay? It's not like every 20 minutes, bam, grow, 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 exactly every 20 minutes. It's just an estimate, it's just an idea. But once you have enough, it looks like they're just constantly multiplying. Let's say that when it came to coronavirus infections, this was based on this exponential growth, a continuous growth model, where if you had one person has corona, he will spread it to, I think coronavirus was like two or three, I can't remember what the number was, but there was a number, R factor, where you could spread it to so many people. I think it was like 2. So these 2 people would then spread it to 2 more people, and these people would spread it for 2 more people. And if you looked at the coronavirus numbers, it got worse like in increments of like 7 to 14 days. You would have these waves that would happen, right? Anywhere between 7 to 14 day waves. And these waves happen, for instance, after Thanksgiving, right? When lots of families gather together, they didn't realize their friends or family had coronavirus. All of a sudden, bam, Christmas, big spike. After Christmas, another big spike, right? And we were afraid because of spring break, we would end up with a big spike. So now it's been about a week, but other groups are still having spring break. So we'll see. The numbers have gone up, but they're not going crazy. Okay. So a couple things. Whenever you hear the word continuous, or you think that's going to be a continuous model, you are going to use this guy here. Okay. Same equation. Sometimes we'll use a different variable. Let's say m is equal to m naught for mass. E equals to RT or KT. So R could be K. It's just a variable, but we're always following the same idea of, let me show you what the idea is. This is our end value. This is our starting value. E to the rate and times time. These are the words that are associated to each of these positions. End is our final value. What happens? How much do we have after everything has been done? Starting is what's the number that we're starting at. The rate is the growth rate given this time interval. And then so if this was, for instance, if the time was days, the rate would be something per day. Okay, these guys would be a match. Okay, so let's use a very popular example of half-life. If we see something called half-life, and we can look at a problem here. Let's see if this is the problem half-life. No, this is not the half-life one. Trying to look for the half-life problem. Here's a half-life one. Let's go ahead and save this first. Then we're going to open it up because I'm afraid that I'll lose it. Okay, here we go. So here's our half-life model. So the half-life of a radioactive kind of strontium is 65 days. How much will be left after 195 days if you start off with 3,776 grams of it? Okay, so let me explain to you what half-life is if you don't remember from chemistry. In chemistry, you have a specific equation, and we'll show you that equation is the same equation that we're talking about here. So the idea of half-life, what that means is if I start with a pile of this radioactive strontium, S-T-R-O-N-T-I-U-M, okay, strontium, and I have 377.6, okay? After 65 days, we will end up with half of it. So half-life doesn't mean like it dies after half that life, or it means you end up with half the amount. And half the amount of 3,776, take out my calculator on my left hand, 3,776 divided by 2, we will end up with 1,888 grams of it after 65 days. That's literally what half-life means. So if you hear the term on the news, or when someone says, oh, the half-life of this radioactive isotope, the half-life from our nuclear power plants is 50 million years, it means it will take that much time not to get rid of it, but just to end up with half of it. Okay? Well then, if I wait another 65 years, we end up with half of this. And that's 944. And then if I take another 65 years, we end up with half of that, which will be, whoops. Oh, sorry, that's a 4. That was a 4. Okay, 9944. And then half of that would be 472. Okay, so it would take us a total of 195 days to get from 3,776 to 1,888 to 949. Okay. So we're looking at this, and the idea is that half-life just refers to after so many years, in this case 65 years, we'll end up with half as much. So the question is, how much will be left after 95 days? Well, 95 days is 65, 65, 65. That's 195 days. So we ended up with going through 1, 2, 3 half-life cycles to end up with 472. Now, do we need exponential growth to figure that out? No, because 195 is a nice whole number, and it is 65 3 times. So we went through 3 cycles of it. But let's do this with our exponential growth model. So here's what we need to do. We know it takes 195 days to get half of it. But do we know what is the rate of decay for just 1 day? Do we know what the rate of decay for 1 day is? We don't. And this is decaying. You know what? We might say it's decaying in half, but I want to ask you this fact. Is it that on the 65 day, let's say I have a pile of this sitting on my floor, just because I have radioactive stuff on my floor, and I wait 65 days, does it all of a sudden go bloop and disappear in half? Is that what happens? And after another 65 days, boop, and then it's like even half of that? Does it just automatically disappear? No, it is continuously disappearing. It's continuously breaking down. The atom is falling apart. It's bonding with other elements in the air. What happens is it's not just all of a sudden, boop. It's not like your bank account where all of a sudden just drops in half. It is slowly deteriorating. It's changing to other elements. It's breaking down. So this is a continuous growth model. So here's what we're going to do. We're going to find out what the rate is, and then we're going to now make a prediction. And I'll show you guys how we're going to make that prediction. Okay. So we're going to write it off as, if I start off with 3,776, okay, our model is going to be m is equal to m naught e to the kt, where m stands for mass. This is our starting mass. This is our ending mass. We're looking for the rate. We do not know what the daily rate is. And the time period, how long does it take us to cut this in half? It's going to be 195 days. So if we start off with 3,776, and half of that is 1,888, why did I choose these numbers here? Well, it's because it's the only time that we have related to it. We know that this will all cut in half in 195 days. Now, if you remember this from chemistry, this chemistry model was this: 1/2 equals to e to the negative kt. That's what your chemistry formula was for half-life. Does that look like what we wrote here? It will, because if I divide 188 divided by 3,776, that's 1/2 e to the k 195. This model, it's the same. Only part that we're going to see is that the calculator will give me a negative k value, which is what we want here. Okay, now here 1/2 is equal to e to the k 195. Folks, if we're solving for exponents, what log can I use to get rid of an e? Do you guys remember what type of log? It's a fancy log. It's a au naturel organic log. Organic, certified organic here. And we see that that natural log cancels out, leaving me natural log of 1/2 equals to k 195. Now my last step is to divide the 195, but I'm going to help everyone right now. Please, everyone on your calculator, please take out a calculator, and I want you to do this for me. Do not divide the 195 yet. Go ahead on your calculator. I want you to type this left part. Do 1 divided by 2. Okay? And then we're going to just go ahead and natural log that right now on our calculator. Natural log that. We're going to do the work on the calculator. And then we're going to divide this by the 195. We're going to bring that over, divided by 195. Why am I asking you to do this way? Because it's less confusing than writing it out. If you wrote it out, it'll be natural log 1/2 divided by 195. And sure, you could do that. And our answer here is negative 0.00355. Let's give ourselves a couple decimal places here. Now this is a super small rate of decay, right? It means every day it's going to decay at not even 1%. 1% is 0.01. That's 1%. This is a third of 1%. And this is our k value. Our k is equal to negative 0.00355. Okay, so I'm trying to keep as many decimals as I can because a small change in your decimal place, especially when it comes to exponents, changes your answer dramatically. So we're going to go back now, and I'm going to create a new equation here. So we know our k value is negative 0.00355. Remember, our half-life equation from chemistry is a negative k, and guess what? We have our negative k value already. So we have a decay rate of 0.00355 per day. And so I'm going to go ahead and rewrite this equation now. We're going to end up with m is equal to 3776. That's the amount that we're going to start off with. Our rate is at negative 0.00355. Again, that's just a rounded off decimal. And then we are going to go for the full 100. Oh my goodness, I wrote the wrong one. Oh my goodness, I used the wrong number. Is 195 my half-life? No, it's not. 195 is what they wanted. They wanted, oh my goodness, I didn't even read this correctly. They wanted 65 to be the half-life. 65. Oh man, so I need to change this. Let's go back and change it now. Oh my goodness. I need to change this. Oh my goodness. This. No one told me. No one caught me. Change all these numbers here. Oh my goodness. So let's go back and change it. So this should have been 65, folks. 65. But guess what? In the end, our calculator work is just 0.5 natural log divided by 65. That gives us a different number now. Now it's 1%. Okay, here we go. So our k value is negative 1.0166. I wrote the wrong half-life number. Our goal is to get to 195. Okay, so please change those to 65 real quick. Now, if I change this to 65, right, this will give us, I'm going to show you guys that this half-life model is going to work. 65. Now, if I plug this into my calculator, I'm expecting after 65 years at a rate at oh, that's the wrong point again. That's the wrong exponent. Our new value is 1 point. Darn it, sorry, that's a 0. That's a 0 here. That's a 0. 0.0166 times 65 years. And that should give us a half of it. Okay. So on my calculator, I always write the exponents first. That's how my calculator works. So, oh my goodness, I even copied it wrong. What's wrong with me? Gosh. Okay, there are a lot of things wrong with me, but I mean, just let's stick to one thing at a time. 0.01066. Oh my goodness, come on. Okay, I'm going to take this exponent. I'm going to multiply this by 65. I'm going to e this value. We have e button here. E that value. Then times this by 3776. We end up with about 1800. No, sir, 1888. Which is half of what we started off with. Now, if I want to predict how much we have after 195 days, 3776 e to the negative 0.01066 and 195 days. How much do we have left? One, no, not one. So let's go ahead and do the exponent. 0.01066 times 195. We're going to have some round off error, please. Make this negative. This is negative. My bad. Okay. We're going to E this number. Then times this by 3776. We end up with 472.35. We're going to have some round off error. Let's go and take a look at what we had before. Nope, wrong one. And if you look at our answer before, we were at 472. 472, which is really close to our answer here. Why do we have 0.35? Because of our round off error. So why do we have to do it this way? It's because on this easy question, we could get from 65 to 195 by going through 1, 2, 3 half-life cycles. But on the SAT, and the skill is not that I can do this without, but you're just counting 3 cycles. That's pretty easy, right? That's like a level 1 problem. But what if I ask you instead, after 1,000 days, after 1,000 days, actually, no, let's do, not 1,000, a little too much because we won't have anything left. Let's see, after 300 days, how much would we have left? Well, is 300 a division of 65? Nope, it's going to be some decimal number. So 65 doesn't go into it nicely. But our problem doesn't change. It's 3776 e to the negative 0.01066. And we're just going to change this to write 300 now. After 300 days, how much would we have left? If I want to find out how, after 1,000 days, how much would we have left? So, I'm going to type it as, I always go backwards. I do exponents first. Negative 0.01066 times 300 equals E this number, then times this by 3376. Oh, 3376, my bad. 3776, darn it. Times 3376. I used the wrong number. Let's do this again. 300 times 0.01066 negative equals, we're going to E this number and we'll multiply this number by 3776. Sorry. And we're left with 154 grams left. 0.22. Okay. So if you remember this from Algebra 2, our goal is to find out what the K value is, and then once we have this rate value, this K value, we can then plug in whatever value we want. The easy questions, as we see in this problem here, we can just cycle through 65 days, 3 cycles down would give us 195. And that's an easy question. Now, that's half-life. That's the model of half-life. We first find our K value, and then we can predict what, using our new date, how much we have left. Do you guys remember doing half-life in Algebra 2? And it's something that we were using logs for. Okay. Now, let's look at this question here. Due to its weakened steel industry, Washington County has experienced a population decline of 5% every year. So it looks like our R value is 5% per year. The current population is P naught, which is the initial population, is 23,600. Assuming the trend continues, what's the population after 7 years? Now, the way that this works is that, is this a discrete or a continuous decline? Is it literally at December 31st, 5% of the people just leave? No, right? So people are leaving continuously, just randomly throughout the year. So if that is the idea of the problem, we have to use this continuous model. So it's P is equal to P naught e to the RT. Now the thing is here, they gave us the rate. And they said, well, isn't T in years? So as long as the rate and our time match, we can just plug everything we need in. P is equal to our initial population of 23600. E to the R of 0.05, right? We write it as a percentage, as a decimal. And the number of years that we want to wait for is just 7. This problem is done from here, as long as you can set up the model to the equation. Now, let me ask you, I made one mistake here. Are we increasing in population or are we decreasing in population? We are decreasing, right? So this K value is going to be negative because we are actually losing 5% per year. And all you have to do is just plug that into a calculator. So I'm going to do 0.05 negative times 7 years. Okay, and we're going to multiply this by E, sorry, exponent of E. And this new number, we're going to times 23600. And we end up with a population of 16,630. Okay, and that's our final population. Now, do you think that's a huge loss in the number of people? Yeah, if you're losing 5% per year, it doesn't sound like a lot. Sure, see you later, we didn't want you anyway. But after 7 years, this is compounded continuously. And to go from 23,000 to 16,000, that sounds like you're losing some neighbors. Now, LAUSD has had this issue when it comes to number of students who are leaving LAUSD. So the population of LAUSD students has been on the decrease because people are moving to Texas or moving out. People aren't having kids. So you can see that if this is a high percentage rate, even at 5%, after 7 years, man, your class sizes might be the same, but the number of kids going to that school has dropped. You can think of this as income. What if this you had $23,000 to retire on? And if you're just using 5% losing 5% every year, you're not going to have much to live off of. Okay. Let's look at another problem here. Okay, let's see if this is something similar. Trent pays $1,331 for a washer dryer combo. Each year the appliance costs 15%, loses 15% to its resale value. How much will it be after 6 years? So this is being compounded, I think, continuously, right? Because it's not like it just loses value in January. So we have a rate of 0.15. Our initial cost, or price, was the original price is 1,331. Wow, that's expensive washing dry machine, because that's just how much it costs these days. And our time is 6%. Oh, 6 years. So to set this up, our final price, our final value of our washer dryer is 1,331, excuse me, e to the 0.15 times 6. And this is going to be negative because it's depreciating. We're losing money here. Calculator. They want us to round to nearest cent. So I'm going to type 0.15 negative times 6 equals, we're going to e that number and then times that by 1,331. And your washer dryer after 6 years is only worth $541.14. Now, I'm not a tax professional, but if you are a millionaire with a lot of property, you can actually count the depreciation of your buildings, because every year they're not worth as much because they are getting old. And you can actually take that as a tax write-off. Again, I am not a tax professional, but you can save a lot of money. If you said, hey, my building's not worth as much anymore, it's getting older, then you can write that off and you pay less taxes on it. Okay. So our last thing, let's take a look at our next assignment, which is compound interest. Now, compound interest has its own set of equations, because compound interest is compounded a discrete number of times, so many times a year. Now, let me give you the equations for compound interest here. Now the equations for compound interest are, if it's basic interest, it's A is equal to P 1 plus R to the T. Right? Now, an example of this, if I say you had $100, initially, that's our principal. P stands for principal, means beginning. Principal, I hope I spelled that right. Principal. And then R is the rate, and T is the time. And let's say you had an interest rate of 3%. Keep dreaming. I haven't seen 3% in years, but let's say you have 3%. If I had $100 at a rate of 3%, and I was able to save this for, let's say, 18 years. Okay, your parents put $100 away in your savings fund just one time. Okay, just one time, never touched it again, at a rate of 3%. After 18 years, would they have enough money to pay for college? I doubt it, but let's see what happens. So we say A is equal to 100, 1 plus 0.03. We change our rate to a decimal, and we're going to take that to the 18th exponent. So this is a straight formula you can memorize. You could also have done this. On your first year, you have $100 and you times it by 1.03. On your second year, you take that number and you multiply that number by 1.03. Then you take that answer and multiply that by 1.03. And you do that for 18 times. That takes forever, right? But that's what this is. We're just multiplying 1.03 18 times. Repeated, 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 repeated. So you write it in this exponent form. If you remember this in Algebra 2, that's how you should have learned it. But let's go ahead and just do this on a calculator now. So 100 times parentheses, open parentheses, of 1.03, close parentheses, but take the exponent of this to the 18th power. And you end up with, is that right? $170. 170.24. I'm going to try that one more time. 1.03 exponent of 18 equals, yeah, $170. Is that enough to pay for college? Nope. But what if you had bought Bitcoin? What if you just bought Doggy Coin? Yikes. Okay, so a low percentage savings isn't going to make you a millionaire. Okay? And if you learn anything about economics, the government can change the savings rate or change the bank rate, which affects your savings rate. So if money doesn't grow very much in your bank account, it actually encourages people to spend. A whole different story. Okay. So here is our next example. This is a per year model. This is happening per year. Per year. But what if they pay your interest not per year but per month? So n times per year. So we have a new model for this from Algebra 2. It's A is equal to P 1 plus R over N to the NT. Now this model is different than our last model because there's an N value now, and that's the number of times they pay you. Number of times they pay you in a given amount of time. So if it's per year, if I pay you 12 times per year, would you think you'll be making more money or less money? Instead of paying you 1 time per year, what if I pay you 12 times per year? Now, what does that mean? If you had $100 to begin with in your bank account, and after 1 month at 3%, you will have, let's see, 100 times 1.03. You would have $103 at the end of not 1 month, but 1 year. But how much do you have after just 1 month? And what we do is we take your number 100, 1 plus 3%, and we divide that by the number of times we are going to divide it by. In this case, 12, for 1 per month. Now, how many years were we trying to pay you off? We're trying to pay you off for 18 years. But since you get a payment every month, you get 12 times 18 now payments. So not only do we change the R on the bottom, sorry, the N on the bottom, which divides the amount of interest you get. Instead of getting 3% of interest at the end of the year, you're going to get 3% divided by 12 per month. So you'll get a little bit more money every month, and then your interest will grow on your new balance and on your new balance. So you're gaining a little bit extra money every single month because you're not waiting till the end of the year to see that money in your bank account. They're paying you out every month. So for this problem here, this is the hard part, plugging this in the calculator. This is where people struggle. So A is equal to 100. And then you're going to write this in your calculator to 12 times 18. That's 216. So 1 plus 0.03 over 12. Now, how would you do this? On my cheap calculator, I'm going to type all this on my calculator first, inside first. 1 plus 0.03 divided by 12 equals. From here, I'm going to take my exponent, xy. What's my exponent? 216 equals. And I'm going to multiply that by 100. And this gives us a total of 171.49. If you look here, because I pay you more often, you now make more money. Because I pay you more often, you now make more money, which is a good thing, right? That's a good thing. And that's how this method changes depending on how many times you are paid. What if you are paid every single day of the year? You don't have to wait every month to make your money. You are paid every single day of the year. At the end of the bank day, you are paid an interest in your account. Do you think you're going to make even more money? Turns out you are, but not much more. If I say A is equal to 100, if I pay you once every day, that's 0.03 over 365 days a year, 365 times 18 years. That's a lot of payments. They got to pay you 365 days for 18 years. That's a lot of payments. But the problem is those payments are for a very small amount of time. The example is imagine if you get paid 10 bucks a day, right? Because your parents say, hey, you get 10 bucks a day. If I pay you every day, you get 10 bucks a day, which is fine. But if I pay you at the end of the week, doesn't it look bigger? It does, right? Don't you get paid like 70 bucks then every week? It looks bigger, but it's still $70. If I pay you 10, that would have been the same thing. Now, but here's what if you do this though? If your parents gave you $10 a day, you went to the liquor store and you bought Cheetos with it, and you came back to Hamilton to sell them. Wouldn't you be making money off that $10 right at the beginning? And then the next day when your parents give you the next $10, you go back to the market and you use yesterday's earnings and the $10 to buy more Cheetos to sell at Hamilton. And then with that money and the new $10 on Wednesday, you go to the market, buy more Cheetos and sell them. And that's the idea of compounding, is that you're taking the money earlier and waiting till the end of the week before you make any money off it. Imagine if your parents just say, you know what, I'm just going to give you the $10 per day at the end of the year. I'll give you $3,000 all at once at the end of the year. Well, that might be cool. You end up with $3,650. But you can't make any of that money till they give you money at the end of the year. So compounding daily is great. Compounding monthly is great, but compounding once a year, that's the worst. Your credit card bill, if you guys did not know, if you guys ever get a credit card bill, they compound the money you owe them, not on a monthly rate. They compound it on a daily rate. Every day you do not pay your credit card company, they will add interest to it. So you are compounded on a daily rate. Those guys want your money. So let's go ahead and type this down on my calculator. 1 plus, let me clear this. And this is the last one we're doing. 1 plus 0.03 divided by 365. Okay. We're going to take this exponent xy of, I need to write this as a parentheses, 365 times 18 equals, that's my huge number, times this by 100. and we end up with 171.59. Did we really make that much more money compared to compounding monthly versus daily? No. If we were talking billions of dollars, this would make a big difference. That's a lot of money. But if we're just talking a couple of cents here, the more you compound it, yes, you make more money, but it doesn't make that big of a difference. We start hitting a theoretical limit. And now let me show you what that limit is. I compound it once a year. I compound it 12 times a year. I compound it 365. What if I compound it every hour? Do you think I'm going to make that much more money now? What if I compound it continuously? And here is your continuous problem again. A is equal to P naught e to the, what's the rate? 0.03, and the time interval is 18. We could take our continuous, we can take our discrete model, month to month, day to day, to what if I just pay you every single second of the year? Now, this is our last problem. This is it. Last one. If I say A is equal to 100, e to the 0.03 times 18. Oh my gosh. This must be a lot of money. Turns out it's not. 0.03 times 18. We're going to e that number and then times that by 100. If I paid you continuously, you would end up with only 1 penny more versus 365, because 365 was a lot already. And if I just pay you literally every second, you're not going to make that much more because the intervals are so short. Okay? So these are the different ways that you can use compound interest, whether you're doing the R over N equation, the standard equation up here, or R continuous. And these are the formulas you'll be using for the homework. Okay? That's it.